Welcome! Today we're going to dive deep into the really powerful techniques we use to teach advanced AI new skills, a process we call fine-tuning.
And that right there is the central challenge. It's all about how to teach an AI that's already a genius something new without messing up everything it already knows.
So here's our game plan. We're going to start with the original big, all-encompassing methods and then journey all the way through to the super slick, hyper-efficient techniques that are really changing the game today.
All right, let's kick things off with the foundation, the classic approach, what we call full fine-tuning.
So what exactly is it? Well, imagine you have this incredibly smart, pre-trained model. Full fine-tuning is like taking that model and just completely retraining it for a new job. We're talking about unfreezing every single parameter, every little knob and dial, and tuning it all based on brand new data.
But, this approach is a real trade-off. On the plus side, you get total adaptation. It's perfect if you're teaching the model something way different from what it was originally trained on. The downside, though, it's hugely expensive. You need tons of data, tons of computing power, and you run into this massive risk of what's called catastrophic forgetting, where the new stuff you teach it literally overwrites all the old valuable knowledge.
So that all-or-nothing problem, it's a big one. And it's exactly what pushed researchers to come up with smarter, more surgical ways to do this. We needed methods that gave us way more control.
So let's break down 3 of these early attempts to get more precise. Think of them as different ways of using a scalpel instead of a sledgehammer.
First up, we have sequential fine-tuning. The name kind of gives it away, right? It's all about specializing the model step by step. You might take a general language model, first tune it on general medical texts, and then narrow the focus even more to just cardiology, for example. It's a staged, progressive process.
Then there's layer-wise fine-tuning. This one is all about getting super granular. A neural network has layers, right? With this technique, you can choose to only tweak the top layers that are specific to your new task, while leaving those deep, foundational layers of knowledge completely untouched.
And finally, we've got feature extraction. Now, this is the most hands-off of the 3. You basically freeze almost the entire pre-trained model. You're just using it to pull out useful features from your data. Then, you just stick a small, new, trainable layer on top. It's incredibly fast, but you do sacrifice some adaptability.
Okay, so those methods were all about being smarter with the data we feed the model. But now, we're shifting gears entirely to a new paradigm, teaching a model by giving it direct feedback from humans.
And that brings us to RLHF, or Reinforcement Learning from Human Feedback. This is a huge deal. It's the secret sauce that made models like ChatGPT feel so aligned and helpful. The whole point is to refine the model's behavior based on what we, as humans, actually like and find useful. It's all about aligning the AI with our preferences and values.
And it works in this really elegant, continuous loop. First, the model generates a response. Second, a human rates that response. And third, the reinforcement learning algorithm takes that feedback and adjusts the model, rewarding it for the good stuff. You just repeat that cycle, and the model gets better and better.
So RLHF was awesome for aligning models, but the underlying problem was still there. Any kind of large-scale tuning was still incredibly expensive. And this constant pressure for efficiency, it sparked an absolute revolution. This is where we get to PEFT.
PEFT stands for Parameter Efficient Fine-Tuning. The core idea is simple but revolutionary. How do we get the maximum impact while making the absolute minimum number of changes? By updating just a tiny fraction of the model's parameters, you slash costs. And what's really cool is, as a side effect, it also helps solve that catastrophic forgetting problem.
So how does it work? Well, a key innovation here is the idea of adapters. Seriously, think of them like little plug-in upgrades for the AI. You take the huge, original model and you freeze it. Then you just slot in these small trainable modules between the layers. Only these tiny adapters get updated during training. It's brilliant.
And one of the most popular ways to do this is called LoRA. LoRA is based on a really clever mathematical insight that the big, complex changes a model learns can often be represented by much, much smaller components. So instead of training the whole giant thing, LoRA just trains these tiny representations. The result? Performance that's shockingly close to full fine-tuning with a tiny fraction of the work.
And when I say a tiny fraction, I mean it. The efficiency gain here is just mind-blowing. We're talking about reducing the number of trainable parameters by up to 10,000 times. That's not an improvement. It's a whole new ballgame. It's a total game changer.
And just when you thought it couldn't get any more efficient, along comes QLoRA. That's quantized LoRa. It builds right on top of LoRa and pushes the efficiency even further. It takes those already super small adapters and compresses them even more using a lower precision format, like 4-bit, which just slashes the memory requirements.
So when would you use one versus the other? It really boils down to a pretty straightforward trade-off. If raw training speed is what you care about most, vanilla LoRa might have a slight edge. But if your main constraint is memory, if you need to fit this on smaller hardware, then QLoRA is absolutely the way to go. All right, for our final stop, let's talk about a method that's super direct, super practical, and has become incredibly popular. It's all about teaching the model by just showing it a bunch of examples.
This is called instruction fine-tuning. And honestly, the best way to think about it is like you're giving the AI a study guide. The guide is just a massive dataset of prompts and the ideal response for each one. You show it thousands or millions of these question and perfect answer pairs, and the model just learns the pattern. This is one of the key techniques behind models like GPT.
So let's put it all together. This table gives you a great bird's-eye view of everything we've talked about. You can see the whole spectrum, from the brute force, high-cost approach of full fine-tuning, all the way down to the surgical precision and incredible efficiency of LoRa and QLoRA. Each one has its place, its own ideal use case.
Ultimately, the evolution of fine-tuning isn't just a story about making things faster or cheaper. It's about becoming smarter and more strategic. We've moved from brute force overhauls to these incredibly precise techniques. And what this really shows us is that the future of AI isn't just about building bigger models. It's about mastering the art of shaping them. The real innovation is in choosing the right tool for the job.